Ever wondered how to evaluate predictive models in machine learning? Today, we'll unravel the mystery of k-fold cross-validation. This technique is a key player in the field of data science, and for good reason. K-fold cross-validation involves dividing your dataset into a specific number of subsets, or folds, and running a series of train and test sessions. The catch? Each session uses a different fold as the validation set. This clever rotation allows for the model to be trained and evaluated multiple times, each time with a different slice of the data. The result? A more reliable measure of the model's effectiveness. By avoiding overfitting and aiding in model assessment, k-fold cross-validation ensures that the model you build is a generalized one, ready to tackle real-world data. Now that you have a basic understanding of what k-fold cross-validation is, let's delve deeper into the process. K-fold cross-validation might sound complex, but in reality, it's a straightforward process. This technique is a staple in the world of data science, helping us fine-tune our predictive models and ensuring they can accurately generalize unseen data. So, let's break down how it works. First, we need to divide our data set into 3 parts: the training set, the testing set, and the validation set. The training set is where the magic happens, as it's here that our model learns to make its predictions. The testing set is used to assess how well our model has learned from the training data. And finally, the validation set is used to fine-tune the model's parameters and ensure that it's performing as well as it can. Now, the key to k-fold cross-validation is the k. This k represents the number of groups or folds we split our data into. It's important to note that k must always be an integer. If we choose k as 5, for instance, we're essentially dividing our dataset into 5 equal parts. Once we've created our folds, we then run our model k times. In each iteration, a different fold is used as the validation set, while the remaining folds make up the training set. This way, each data point gets to be in the validation set once and in the training set k1 times. For example, if we have 5 folds in each iteration, 1 fold, or 20% of the data, is used for testing, and the remaining 4 folds, or 80% of the data, are used for training. We then calculate the accuracy of the model for each iteration and average these values to obtain a more reliable measure of the model's effectiveness. This process allows us to avoid overfitting, a common issue where a model performs well on the training data but poorly on unseen data. By validating our model multiple times, we ensure that it can generalize well to new data, making it robust and reliable. Understanding the process is key to fully grasping the concept of k-fold cross-validation. This powerful technique is an essential tool in any data scientist's toolkit, helping us build models that are not just accurate, but also reliable and robust. Like everything else, k-fold cross-validation has a life cycle. Let's dive into the heart of the matter. Imagine we have a data set and we're working with a k-value of 5. This means we're splitting our data into 5 subsets or folds. Picture it as a pie, sliced into 5 equal pieces. Now, we're going to run the train and test process 5 times, each time using a different slice of the pie for testing, and the remaining pieces for training. In the first iteration, we take the first slice for testing and the remaining 4 slices for training. We run our model, it learns, and we test its performance on the test slice. We get an accuracy score and jot it down. In the second iteration, we take the second slice for testing and the remaining slices, including the first one this time, for training. Again, we run our model, test it, and note the score. We repeat this process until each slice has been used once for testing. That's 5 iterations in total. We now have 5 accuracy scores. What do we do with these scores? We sum them up and calculate the mean. This average score gives us a robust estimate of how well our model is likely to perform on unseen data. Remember, each data point is used once in the holdout set and k1 in training. This is the essence of k-fold cross-validation's life cycle. Just like any other technique, k-fold cross-validation comes with its own set of rules. Here are a few thumb rules to keep in mind while working with this method. First, the k in k-fold should always be greater than or equal to 2. This means that we should have at least 2 subsets or folds of data to work with. If k equals the number of records in the dataset, then we have a special case known as leave one out cross-validation, or LUOCV, where one record is used for testing and the rest for training. Second, the optimized value for k is usually 10 when dealing with a dataset of good size. This is a commonly used standard, but it's not a hard and fast rule. The choice of K depends on the specific characteristics of your dataset. Third, if the K value is too large, it can lead to less variance across the training set and limit the model currency difference across the iterations. In other words, having too many folds might make your model less sensitive to changes in the data. Fourth, the number of folds is indirectly proportional to the size of the dataset. If your dataset is small, you might want to increase the number of folds. And finally, remember that larger values of K increase the running time of the cross-validation process. Hence, it's a balancing act between accuracy and computational efficiency. You might be wondering, where and why do we use K-fold cross-validation? Well, it's a valuable tool in the machine learning field with three primary applications: model selection, parameter tuning, and feature selection. Firstly, model selection. K-fold cross-validation helps us evaluate different predictive models on our data and select the one that performs the best. This ensures we're using the most effective model for our specific task. Secondly, parameter tuning. Through K-fold cross-validation, we can fine-tune our models by adjusting their parameters for optimal performance. It's like fine-tuning a musical instrument to get the best sound. Lastly, feature selection. K-fold cross-validation assists in identifying which features or variables in our dataset are most important for predicting the outcome. This helps us focus on relevant features, reducing noise and increasing model accuracy. So, to sum up, K-fold cross-validation is a valuable tool for evaluating predictive models in machine learning. It's all about understanding the process and using it effectively.